In this video, I'm going to show you how to build an event tree using the binomial distribution. So we're going to begin with a simple question. How many Tainer gates in the district will fail to operate properly this year? Now all the data that you're going to see are made up data. So we begin with n. That's the number of Tainer gates, and it's a total of 200. I'm going to put that here. We see the first question we ask is there metal fatigue, yes or no? Notice that the probability of metal fatigue is 0.21, so I'm going to enter that here in the model, 0.21. Now I have a problem because the two branches do not add up to 1. So I'm going to fix that problem by going into here and saying equal sign 1 minus this value. So now if I ever change that metal fatigue value, the probability of no metal fatigue will automatically change also. The second branch after this node, the second node, is whether the gate fails or not. Now notice up here that we have the probability of failure given metal fatigue is 0.15. So I'm going to enter that here. Once again, I have to assure that my probabilities sum to 1. So here I'm going to put equal sign 1 minus this probability here. Down here I enter the probability of failure with no metal fatigue, and that's 0.05. And when I fix the probability, I get equal sign 1 minus 0.05. So, what we're going to do now is we're going to enter a binomial distribution. Here we have 200 Tainer gates, and we know the probability of metal fatigue is 21%. But we don't know exactly how many of 200 gates are going to have metal fatigue. We're presuming that this 21% would be a value perhaps nationally, and we're applying that at the division level. So we've got some natural variability here. We might be above or below that value. So in this cell right here, I'm going to put my cursor, and I'm going to go to the at-risk tab, and we are going to enter a binomial distribution here. So I double-click the binomial, and I'm going to use my Excel reference, and I'm going to say find the n right here, find the p right here, and I'll leave the static value as 0. The distribution comes up, I click OK, and it closes. So you can see here 21% of 200 is 42, but in this case we're saying we could have 39. We might be a little bit below that national average. I have to fix the number of gates as well here by saying equal sign 200 minus this number tells me the number of gates that have no metal fatigue. And you'll notice when I hit enter, we got another simulated value. So as I hit my F9 key, you can see the different numbers of gates that could have metal fatigue. So now we go to, does the gate fail given that it has metal fatigue? So of these 42 gates that have metal fatigue, I want to know how many of them do I put here and how many of them do I put here. And we're going to use a binomial distribution. Think of that as a switching distribution. It directs a number of the 42 up this path and a number of the 42 down this path. And it uses natural variability to do that. So I'm going to put my cursor in here. I'm going to once again select the binomial distribution. Double click on it. And I'm going to use my Excel references and say, this now is the n, and this now is the p. Static value of 0 is OK. Shows the distribution, and I close. And now I have 4 of the 41 fatigued gates actually fail. And down here I have to have the complement, and that is equal sign 41 minus 4. So notice this number and this number, 10 and 45, must always equal this number. And 55 and 145 will always equal 200. So now we're down to here. I want to know, of these 145 gates, how many of them will fail? So once again, we have a switching function. How many of the 145 will go up here? How many of the 145 will go down here? I put my cursor here, go to define distributions, where I'm going to choose a binomial distribution. And once again, I'm going to use the select. I have 145 as the n, and p is 5%. Once again, static value of 0 is okay. It shows the distribution. I click OK, and we see we have 6 of the 159 gates that have no metal fatigue will fail this year. I have to put the complement down here, equal sign. This minus this. And that's because the numbers keep changing. So now you'll notice I have 3 binomial distributions. One that tells me how many of the 200 go this way and how many go this way. One that switches for this, and one that acts as a switch for this. Now, precision tree is not built explicitly to be used in the fashion that we're using it right now. So what you're going to have to do to make sure you have no problems is you're going to have to override the functions. In here, when I click in this cell, you notice up here in the function line, there is a hidden sheet where a calculation is done. What we want to do is we want to override this, and we're going to put in our own function. We're going to say equal sign. This number is this times this. Okay, this value right here, we're going to say use the value that you see right here. So once again, I'm going to say equal sign this probability times this probability gives me this probability. Now I have 43 here, and that's the number I want. What precision tree is doing is it's back solving a decision problem, and we don't have a decision problem. We have just a pure chance event tree. So all I'm going to do is say equal sign, take this value right here and repeat it, the value in E17, and it does. So I'm going to be doing the same thing here with the remainder of this graph, this model, I should say. And we're going to do equal sign, take this, and one last multiplication. This times this equals this, and equal sign, take this value right here. So I have built the model, I've put binomials in, I've overridden the default calculations that precision tree does, and now I would be ready to answer that question. But you'll notice we don't know how many gates will fail. Here we see 6, but it could be 3, it could be 5, it could be 10, it could be 6, and that's because we really don't know what percent of, or we don't know how many of the 200 gates actually have metal fatigue, and we don't know how many of those will fail. So I'm interested in this number here, that's a failure, and this number here. So let's add those. And we'll call these failures, and I'm going to say equal sign, take this, and add it to this. And now I'm going to make this an output for my model. We're going to do an iteration of a simulation of 1,000 iterations. Okay, so we've got multiple processors here, and we have to turn that off. That was probably a good little diversion because it's likely to happen to you as well. So as our simulation begins, we see we're dealing with a discrete random variable here, whole numbers of gates. So far I have a minimum of 4, a maximum of 28. Now I have a minimum of 2. We're almost finished with the simulation. And there's your answer. We don't know exactly what number of gates will fail. The average number is 14.2. But it could be anywhere between 2 and 29. So your challenge is going to be to use the data and all that you've learned to describe the answer. But let's go back now, because I want to review one more time what we've done. We have a question to answer. We have some data inputs here. Using these data inputs, we constructed an event tree. Then we went back and put in the data inputs. We made sure that we obeyed the laws of probability. And then we went in and built binomial distributions. This binomial distribution says I have an n of 200 and a standard deviation, and a probability of 21%. And so we could get any outcome like this. I could blow this graph up, but to save time, I won't do that for you. But we certainly could take a closer look at that graph. And we've done the same with each node. We have a switching function. The binomial distribution is a switching function for this node, and we have a binomial distribution here that is a switching function for this node. We've identified the outputs we're interested in and captured them. Now there's one other thing that we could do, and that would be if we didn't know the percent that have metal fatigue, we could go in here and, for example, let's just pick a uniform distribution and say it was somewhere between 0.15 and 0.25. The static value is just what you're going to see if there's no simulation being run. So when I click on this and say OK, there is a simulation being run because we have our dice on. If I turn the dice off, you see all the static values show up, 21%, 0, and so on. When I click the dice, we get sampled values. So now I'm saying not only do I have natural variability, but I've got some uncertainty here about the presence of metal fatigue. We could do the same thing for each of these values. I could make this again, I'll use uniform just because it's the quickest and easiest. 0.1 and 0.18, let's say. The probability is uncertain. We believe it's somewhere in there. And now if I go ahead and I rerun my model, I have natural variability that I had at the beginning, but I'm also going to have knowledge uncertainty because I don't know the probability of metal fatigue, and I don't know the probability of failure given metal fatigue. And so I'm going to have a slightly different answer this time. So being able to incorporate a binomial distribution into an event tree gives you a very powerful tool. It gives you a way to capture the natural variability in a model, and that's what you're going to be doing with the exercise that you have in this mod. You'll be applying